Today, we're going to talk about what makes prostate cancer cells metastasize. Basically, why does prostate cancer kill us? We're talking with Dr. Ellis. Hi, Dr. Ellis. How are you doing?
Hi, Darryl. Good, thanks. And thanks for the invite.
Sure. So why don't you tell us what you do and where you do it?
Okay, yes. So at the moment, I'm currently faculty at Cedars-Sinai Medical Institute within the Cancer Center there. I go by a couple of hats that I wear, which is associate professor within the Department of Medicine, Division of Medical Oncology. And I'm also the scientific director of the Center for Urologic Research Excellence.
And what does that mean when you wake up in the morning and when you're able to go to work? What actually are you doing there?
Right. Yeah. So as a basic researcher, our fundamental purpose is to, for me, I identify more as a translational basic researcher. And what that means is I get up every morning and try to fill in gaps, answer clinically relevant questions that will enable us to give mechanistic rationale for the initiation of first-in-human clinical trials.
So mechanistic rationale means what?
Yeah, okay. So as you deferred in our sort of your introduction, we're very interested in understanding and the early identification of a prostate cancer patient that has the potential to metastasize. And as we know, once a prostate cancer patient has metastasized, then we're in very murky waters of really helping that patient survive their disease. Now, of course, outcomes can vary from, sort of short term to long term, but what we really don't have an understanding of is those mechanisms that are allowing a prostate to escape its primary site to where it's usually just within the prostate gland and become lethal to the patient. And so we try to learn and we create models that represent metastatic disease and sort of study the genetic sort of gene regulation makeup within those models and also cross-correlate that with patient data. But then we try to bring that information all the way up to the front and ask, when a patient is diagnosed with a primary prostate cancer, can we see any molecular identities for us, gene regulation patterns that would say or tell us that patient within that 5-year period of initial therapy, being either prostatectomy or radiation, whether that patient is in real danger of becoming that return patient that is now diagnosed or re-diagnosed with metastatic progression. And for us,
Well, let's just stick on that for a second, because that's like sort of like, I don't know, the golden coupon and the chocolate bar. What, if guys get diagnosed with prostate cancer, if the prostate cancer just stays within the realm of the prostate, you may end up with a big prostate and have urinary difficulties and such, and but you're not particularly going to feel much distress, if any. The problem with prostate cancer is when prostate cancer metastasizes to other parts of your body. So really, the goal of treatment is less about like removing cancer or this or that. It's about keeping the cancer from killing us, because we could sort of live with it.
Yep. So that's true. And yeah, that comes into a sort of a secondary line of questioning when looking at primary diagnosis of these cancers. Firstly, I think, the cancer word obviously would almost put panic into anybody when they hear that word, and that's understandable. What we would like to eventually give is the patient, you are diagnosed with prostate cancer, but it's either in two categories, to where we've got indolent, as you were describing, where a man can just live with that cancer for the rest of his life and no real intrusive action would be needed therapy-wise, or those men that would be deemed aggressive. And that primary prostate cancer is going to be the one that does metastasize sort of within that, 5-year window, and then become a lethal or life-threatening issue for the patient. So it is still sort of like the holy grail question, in my opinion, when it comes to primary prostate cancer. We are getting better with some of the technologies that are now, entering into the clinical space. And as a researcher, it's great to see these, discoveries entering. And one of the biggest ones lately is in the theranostic world, where PSMA imaging, PET imaging has become something of a whole new level for diagnosis and prognosis for these prostate cancer patients up front and early, but also can give the patient a better look at their overall burden of disease, to where they might just be thinking we've only got primary cancer, but really there is sort of early metastasis already starting to occur. And why the metastasis, could be treatment naive and still very early in its progression, we could still have a chance of stopping things from becoming a lethal issue for the patient.
All right. So let's today talk about two sort of basic but absolutely hypercritical things. One, what is it that prostate cancer is, meaning from your point of view? What does it look like? What does it feel like? What conversations do you have when you're at work with the cells that are in front of you? And we'll discuss that in a second. And then forget PSMA and all this, stuff that we're discussing in other videos and conversations with other doctors. What is it that in your world, in your lab bench world, what are you trying to do to stop a prostate cancer cell from metastasizing to some other part of the body and kill us? So and not to get off the track, but you mentioned the word theranostics, just like in 15 seconds or less. What is that?
Okay, so theranostics is a form of radio-labeled. Can we edit that?
No, I'll take care of it. I'll put in a definition below, and really it relates to how we sort of utilize radio emitting particles to sort of attach an image to cancer cells.
Yeah, I can't just put it into lay terms. I'm wondering if we could just skip over that, because all I'm having coming out of me right now was science.
That's okay, because that's human, and it's ridiculous to start pretending that investigators and doctors aren't human and always have the right thing to say at the right moment.
Right.
But let's return to what's on the table today. When you get to work, you're looking through binoculars, you're looking through a screen, you're looking at cells and tissues, and then you're manipulating them. What is it? Is that correct?
Pretty much, yeah.
Okay, right. So you got cancer, and one of the cool things about people, cancer biologists, pathologists, folks who actually look at slides of samples of people's bodies. You actually have contact with cancer. You're seeing it, if it had any scent, probably does on some level, but if, you'd be smelling it. If it had a mouth, you'd be talking to it. If it had a violin, you'd be listening to it play. What is it that when you're sitting, after years of your experience, what is your relationship? What do you see? Is there a beauty to when you look at a cancer cell, a prostate cancer cell? What's going on there for you?
Right, yeah. Well, in a way, there has to be a respect for cancer cells just in a biology sense, because what we're really looking at is a normal cell that has a set of instructions to go from stem cell to a differentiated cell of a certain identity. In our case, we're looking at a cell that becomes a prostate secretory cell. And so these are the cells that function normally in a man's prostate that will secrete things like sperm and God, I'm just forgetting all my words now. But yeah, I just got. Ugh.
Well, that's not what the process of the cell is actually sort of a sidebar thing as well. What I'd like, patients want to know what's going on inside, and you and your colleagues are the only folks that actually visibly see what's going on inside on a molecular level, on a cellular level. What is it that what are you looking at?
Right. So basically what we're looking at is a good cell gone bad. And we look at this at the molecular level and how genes are regulated. So we have a normal cell that has a certain gene regulation profile that tells us that this is a normal prostate cell. But when we come to cancer, we have a different gene regulation profile. And basically what this is, in simplistic terms, and which I prefer, is the fact that we have certain genes of value that are considered oncogenes or cancer promoting, and another set of genes called tumor suppressor genes, which are obviously anti-cancer. And the basics in the cancer cell is that cell has found a way to switch on oncogenes and switch off tumor suppressor genes. And that's a form of molecular interplay, if you will, to where gene regulation patterns have gone wrong. We look at a specific mechanism which has really just come to the forefront within the prostate cancer world, and also some other disease sites, to which this cell identity, when a prostate cancer is present, it can still be identified as a prostate cell. But what we've now come to learn is there's even more, another level, if you will, of aggressiveness, to where this prostate cancer cell can de-identify itself and make itself look like potentially another cell. And so it's no longer be recognized by the immune system. It'll no longer be recognized by our current therapies as well. And so the way this cell seems to act is it will switch from its prostate sort of focused gene regulation patterns on the cancer level and switch to something what we refer to as neuronal-like or stem-like. And so it almost reverts itself back very, very rapidly, sort of backwards in its developmental process. And this is sort of scary because right now we don't have anything to successfully treat these types of cancers or prostate cancers that are doing this. And that's where my research really focuses on. And so it's basically down to two questions: is when these molecular events of this cell losing its identity and becoming very aggressive and dangerous, is firstly, can we identify it and identify it early to see whether the patient does have this within their primary disease? And secondly, if the current standard of care therapies that we do have are not going to treat or successfully treat this cancer, then what experimental approaches can we try in the lab to hopefully then translate to clinical trial and a new standard of care, maybe even in a precision medicine fashion, to get this patient the best treatment for their specific prostate cancer?
So right today, we know what things are going wrong or what we'd like to change. We just don't really have a sense on how to change that. Is that fair to say?
In some circumstances, yeah. When these cells go severely to the left with these cell identity change mechanisms, it's murky waters. We don't have a real grasp at the moment, but we're getting there. We're going to get there rapidly because of the collective minds that are on this problem right now worldwide.
Great. And let's not get too political, whether the cells are going to the left and that's a bad thing, or going to the right to the bad thing.
Yes.
They're just going crap. You know, we're so
that's the way of putting it.
Right. See, so when patients talk about we see something, they're thinking MRIs, CAT scans, bone scans, and stuff like that. You and I are talking at a whole different world now, right? We're not talking about scanning. We're talking, this is more like astronomy reversed.
Yeah, we're getting down deep and personal with the individual cancer cell. And so the way we look at this at the molecular level is we will take a collective of cells and sort of the way it's almost the way we used to do it is we would just take a collective of cells. We would collect the chromatin or the DNA or the RNA from the cell. And this is the code by which the cell runs gene regulation and creates cell identity, and or the blueprint for the cell to become what it's meant to become. And we will sequence the DNA or the RNA, and we will look at it basically at the nucleotide level. So we will look at it, base pair by base pair by base pair, and that gives us an overall molecular profile of what genes the cell is switching on and what genes the cell is switching off. We can also go to another level to where, by these gene regulation patterns that are in front of us, following our sequencing experiments, we can start to understand what potential master regulators are driving those gene expression patterns and what pathways are involved in the overall cellular program that is allowing these gene regulation patterns to take place. And that's where an idea or a therapeutic approach can come into play, because we may already have a drug that's even used in another disease that may be able to come over and help these prostate cancer patients. Or we may go into a direction where we don't have a drug, but we have to go into drug discovery and hopefully come up with something from our smart chemists that we do get that new drug that then can come into the clinic. That's a long process, but that's sort of the overarching goal for there. And ultimately, if we have the perfect picture, what we're therapeutically targeting can also stand as a biomarker. And so in that way, that biomarker can be detected. It's a known actionable target, and that means that we have a therapy to now hit the biomarker that we're looking at as well. That's so.
Part of this kind of interview thing, I have like 1,000 people sitting behind me, knocking on my shoulder, whispering in my ear, lots of questions and such. And the first one that comes to mind, is based on what you just said, is if we're looking at existing drugs, seeing if we could repurpose them to affect prostate cancer, the whole mechanism of metastases, et cetera. Why is that taking so long? I mean, there aren't a billion drugs on the planet. Why not just gather, spend a couple of $1 million, go to the glass store, get a bunch of Petri dishes, and just spend a month or two pouring various chemicals into these things and see what happens?
So I think the biggest pitfall that we have to get at right now, and this is really, it's actually in both blood and solid forms of cancer, is tumor heterogeneity. And so that's where the previous thinking of cancer was that it was one cell gone bad, and then it just makes millions or billions of copies of itself. So we're dealing with billions of cells that all come from one mothership, so to speak, and so everything's the same. But what we're now learning is that when we take these billions of cells and we're now allowed, or technology has allowed us to look at every cell individually, we now know, and we've known this for a few years now, that every cell can be potentially different. And so when we get a target, maybe in a low percent of cells that can be targeted today, it doesn't mean that there's another set of cells right next to it that'll be resistant to drug A, and that will now grow out and become the problematic cancer for the patient. And so with heterogeneity becomes a whole nother level. This heterogeneity, it's a whole nother level of issues. So instead of coming at this with just, a one drug at a time approach, a lot of us now, both in the clinic and in the research lab, we've got to think in combination strategies. And so it's almost like a boxer's combination with, jab, jab, cross sort of thing. And it's like, okay, we have multiple tumor sort of cell identities, if you will, representing this heterogeneity. And if drug A can hit this class of cells over here, and hopefully then we'll understand that there'll be a drug B and a drug C that we can potentially hit the remaining cells after drug A works. I hope that makes sense. But this is where we can then hopefully approach the patient. And what I would love is to be able to approach a patient on an individual level and just basically provide individual patient information, molecular information about their tumor, and come up with a personalized or a precision plan for them therapy-wise. And that could involve a combination of surgery with like experimental targeted therapies. But what that would allow is to cast a wider net and then hopefully grab the cancer all at once and bring it out, or treat it successfully. And that would be, where we sort of see our holy grail, if you will, for what we could provide for the patient from working at the bench every day.
Yeah. And is there anything that the body is doing, quote unquote, naturally, or has been designed to do to impede metastasis?
Yeah, well, the body, of course, doesn't want something where it is not supposed to be, or a cell of a certain origin not supposed to be. So, firstly, of course, we've got our immune system, but we know at the moment that prostate cancer has some secret key to really evade the patient's own immune system. We're looking at better ways to switch that on. With immune therapy has really made a big splash in the world of therapeutics now, over probably the past 10 years. But prostate cancer at the moment is not the best responder to these. So we've now got to figure out, and coming back again to combination strategies on what therapy can awaken the immune system within the prostate cancer patient to use the current immunotherapies and also new immunotherapy strategies coming through. That's sort of the way we're looking at it in my lab. But other ways and other ways people can look at it is also, things outside the body affecting the body, and that's obviously environment. And so people are looking at the ways the environment can also inflict certain advantages, if you will, to a cancer, to where it is enabled to escape and become problematic distally or from a metastatic perspective. But there's numerous ways, and I think that the third way that I'll sort of say here is, I guess, just the intracellular working of the cell and how it manipulates that cancer cell and how it manipulates its direct surroundings to even make other cells, not act the way they normally would. The immune cell is a perfect example of this. A tumor as a whole, a cancer, can actually, and what we think in prostate cancer, it's able to almost like hypnotize the immune cells and basically have immune cells there that provide support for the cancer progression or growth rather than providing anti-tumor activity. But also immediately within its environment, especially in the prostate gland, there's certain cellular barriers that the cancer has to get through to escape the prostate gland and then become metastatic or spread around the body. And so it's turning on or acquiring certain molecular properties just within the tumor cell that allows it to degrade or get these cellular barriers out of the way and allow the cancer cell to get into the bloodstream, survive in the bloodstream, and then get through to another organ like the bone, like the liver, and then survive and grow to become a metastatic problem. So unfortunately, there's just not one answer here, and there is multiple sort of ways a cancer cell can get to this from sort of A to B.
Yeah, but that's good that there's more than one answer, more than one question, because if we're wrong, there's another avenue to check out.
That's right.
If it's binary, we're screwed if we're wrong.
Yes.
I mean, that's species extinction time,
That's right. Yeah, that's a good point.
So we'll talk about environmental influence, which is to say diet, physical location, impact of, working in a nuclear facility or a farm and being exposed to pesticides and stuff in a brief second, to the extent that you're aware of things like that. But metastases is sort of a global way to say you got cancer cells that are going to go someplace else and be some other cell. And because of that substitution or disguising, it causes death. What makes a prostate cancer cell choose or cause to migrate to, let's say, a bone versus a brain or a toe versus a finger?
Yeah, where does it metastasize is a big question, and we fully still don't understand that, to be perfectly honest. We cannot take a primary cancer or prostate cancer, look at it, and if it's got a metastatic signature already embedded in there, we can't say this metastatic signature is specific for bone progression, for liver progression, or anything like that. We just can't. This is what we want to do, but we just can't do it at the moment, at least to my knowledge. But I think also with the cancer cell, as I said, a normal cell has a set of rules that defines it to go from stem cell to differentiated cell. And if it doesn't get to that differentiated cell in a normal context, it's then also programmed to kill itself. And all these rules are switched off in a cancer cell. So I think if you imagine a cancer cell with no rules, and it's almost genetically or molecularly dabbling in different cellular signaling combinations within the cell to give it the best survival benefits, clonal fitness, if you will, to enable its escape from therapy and its escape from the primary gland to become metastatic. And I really think it's just like if you have, let's say, 1 million cells that hit a patient's bone, it may only be 10 of those to 100 of those that actually acquire the right molecular program just by testing the waters in the new environment that give it the fitness to allow survival and growth and metastatic disease.
We describe it in our support groups as like the hunt for extraterrestrials. There are enough planets, enough galaxies, enough star systems, and et cetera, that numerically it's just likely / plausible that there are other people out there, or at least, other sentient worms or something. I think it's good to be able to visualize that there are lots of cells that are leaving our prostate that are still not going to cause us harm.
Correct. Yes.
Yeah. And, one of the holy grails we've considered at Malecare is, what if we could direct the process of metastases to something benign or something survivable, perhaps something that may require an amputation or something, but you still get through the rest of your life, or something, or some sort of therapy, a kidney transplant perhaps, or something. That would be cool. And the work that you're doing or that your colleagues are doing might lead to that as a remedy rather than trying to do the process, understand therapeutic processes and refine them in the ways that we've been doing the last 2 decades that still have yet to really bear fruit and save us. The patient concern about what can I do? Let's do the basic stuff. What do you know about sugar?
What do I know about sugar? Sugar, I really hate to discuss metabolism because I come from a different background where I competed in bodybuilding for many years. And so I use food in a different way than I guess the normal average day person. But sugar to me, I always discuss this with an individual manner. I don't like to throw nutrient blankets, if you will. I know there's studies out there that say sugar's bad, and I know that there's studies out there that say, well, sugar's not so bad. And the same can be said for fats and high protein diets. I don't know if I can.
Okay. So let me approach you in a different way. What environmental influences, whether it's concrete things like, Agent Orange or burn pits for veterans and such, or for military folks, or pesticides for farmers, or, metal workers, or have different exposures, or dietary things, or physical location, should we all move to Greece or something? What can you share from your lab bench world that could provide something?
I think, and a way I'll tell you how I approach myself is that we know with age, the prostate, naturally becomes inflamed. Most older men will have a form of, inflammation or benign prostatic hyperplasia within their prostate. And I tend to look at this from the concept of trying to not intake so many inflammatory sort of foods. And one of the biggest ways for me is that rather than putting in a high amount of saturated fats, which for me would have come from a lot of red meat intake or certain cuts of chicken, things like that, which come with that, nice white fat that you can see very easily. I've limited that, and I've put more of a good fat or a mono unsaturated type of fat, which comes usually from nuts for me, like cashews, almonds, things of that nature, and even your cooking oils. I think that's, again, I don't want to tell people what to do. I leave that to the clinicians. But that's just one of the sort of generalisms that I apply to prostate and just overall body inflammation as well. But one thing that we still don't know, or at least for me, I'm not satisfied with our knowledge of inflammation and initiation of prostate cancer, and sort of a chicken and the egg story there as to, will certain chronic forms of inflammation induce a molecular switch in a prostate cell to create cancer? Or is it just the prostate cell itself creating cancer with this molecular switch and then synergizing with the environment, which is could at different levels of inflammation, is that then coming together to make an indolent or an aggressive prostate cancer? It's something I think about, but it's just something in that context from a dietary perspective that we're not tackling in my research, because there's so many other great people around the world doing that. We have a different expertise with how we approach things.
Three more questions, and then we'll let you get back to your bench. Actually four. What does your T-shirt say?
So this is sent from my mother. It's just to remind me of where I'm from.
Cool.
Yeah.
Cool. Are you a Wallaby supporter?
I've been rugby league and rugby union fan for as long as I can remember. You grow up, playing football or rugby in some form in Australia. So 4 years of age was my first game.
Wow. Very good. Very good. So there are two terms and then one question. You've mentioned the term differentiated. I know what that refers to. You mentioned the term switch. Why don't you just, for our patient audience, when an investigator, when a doctor says differentiated versus undifferentiated cells, when they're doing the Gleason charts and this and that, right. 90 seconds or 50 seconds or less, what does that refer to?
Okay, so simplistically, from a differentiated perspective, as a normal prostate forms, it forms glandulary ducts that secrete from the prostate into the bloodstream. And so when you look at this under a microscope, you will see these nice ducts throughout the prostate that have a certain appearance about them to be normal. In a prostate cancer, or even a precancer, a prostatic intraepithelial neoplasia, or PIN, some patients might have heard of. This is where the cellular structures become disorganized and the space within these glandular ducts, start to become filled. And so this is a disorganization of the cellular structure within the prostate. And then when you go to that'll still be considered some form of differentiation, because you can still make these glandular ducts out. But when we then go to the undifferentiated state from a morphology perspective, this is where you look at a prostate, and basically the glandular duct formations have gone, and you're looking more just at a sheet, like a flat sheet of tumor cells mixed in with some of the like stroma cells, the myofibroblasts that also make up the prostate gland. And so it's really, looking at the structures that form normal prostate to the loss of these structures, where you're just looking at a sort of a flat sheet of cancer cells.
Okay, thanks for that. And switch.
Just want to say I'm not a pathologist, not a clinical pathologist.
Right.
This is just coming from a researcher perspective that thankfully has some great pathology mentors and friends.
Look, if Homer Simpson knew how to describe differentiate versus undifferentiate, that's valid too. What does the word switch refer to in your world?
Okay, yeah. So I think the easiest example I could give of a molecular switch is a normal prostate cell that we're talking about that becomes cancer. It's actually driven by a receptor, the androgen receptor, which drives this sort of transcription or gene regulatory program that drives just the normal prostate cancer to adulthood, if you will, or differentiation. And basically, it's considered a good guy because it's doing what it's supposed to do and it's driving the identity of that cell. But when a molecular switch happens in one of these prostate cells, and it could be the loss of a tumor suppressor gene like P10 or the gain of a cancer-promoting gene or oncogene, c-MYC, and patients may have heard of these genes related to their cancers as well, that molecular switch there, by just having a tumor suppressor gene turn off or a oncogene turn on, that there is remodeling within the cell and the androgen receptor takes on new gene targets. So there's a sort of a dual program now going on where the androgen receptor will still drive a certain cell identity that we know it's a prostate cell, but we now know it's a prostate cell gone bad because there's a secondary set of genes that have been switched on or switched off that shouldn't be on or off. And so this switch is now the androgen receptor becoming a bad guy. And many patients would have been through the therapeutic sort of chase of trying to inhibit the androgen receptor or the androgen biosynthesis pathways that fuel the androgen receptor's activity. And I think that's probably the best example of what a molecular switch would look like, just sort of taking the androgen receptor as a good guy and turning it into a bad guy. So one that drives just normal cell differentiation to one that's now driving cancer progression.
Yeah, and that's actually a very well-stated description of the mechanism. And for those of us who need to hear that again and again, thank goodness this is a video that you could repeat over and over again, even this small section, so you get it. It's important for us to know what's going on in our bodies and also to know some of the language and lingo that our healthcare providers use on a day-to-day basis. That's like a foreign language to the rest of us. So, just getting a bit savvy on that makes us smarter patients and, just keeps us alive a couple of extra days, I think, so. Yeah. So, and last question, and then, and remind our audience, please hit the subscribe button, hit the like button. If you don't like this video, hit the like anyway and the subscribe anyway, so that, we'll try and do better. But we got to train YouTube to sort of respect cancer focused videos. And the only way to do that is to build an audience to show them these kind of things are important too, in addition to travel and gaming videos, etc. So you got a bunch of investigators and researchers in one room, a bunch of pathologists in another room, a bunch of medical oncologists in another room, radiation oncologists in another, or radiation oncologists in another room, a bunch of surgeons in another room, and maybe nurses and social workers in the gym on the second floor. Who's going to live based on what each of these disciplines know today? Who's more likely to outlive prostate cancer diagnosis based on their profession?
Oh, geez. I don't know if I want to point the finger there at anyone. I'd like to think with the current development in radiology and, maybe the rad oncs jumping into their sort of imaging machines might have a better chance at earlier sort of diagnosis, finding something earlier. But, you put me in a corner here, Darryl.
Yeah. No, New Zealand's All Blacks will put you in a corner.
I love you all, and you're all equally important. But I don't know. I'd like to think that we'll all communicate with each other whenever there's an issue come up, and we use that multidisciplinary approach to come up with the best and fastest answer to squash it.
Yeah, I mean, I kind of think it's the social workers, but that's just my own sort of thing. So
we might have to elaborate on that.
Because the social workers know about we're about. I mean, that's my profession. So we're about keep enjoying life. That no matter what bus may be lurking around the corner to run us over and kill us. If we keep enjoying life, we're winning, we're succeeding, we're enjoying life. If we're focused on the mechanics and methodologies of survival, maybe we're not going to be as happy as if we're listening to the music and enjoying the sunshine and scuba diving or whatever. Enjoying food.
Something we didn't discuss in this time, but also family history is something that is really important when it comes to early diagnosis as well. And if you don't mind me saying, because I'd love to just be able to reach the general public with this, is we know that there is a race disparity with prostate cancer, and where we are currently in the lab is we lack disparity within our models, and we're trying to make better models to both represent Black men, white men, and all men, of the rainbow, so to speak. But if I could just urge the help with enrollment in clinical trials from all patients, just so we can better represent everybody that's facing the same challenge of prostate cancer. That would be fantastic, and whatever we can do to help that, I'm happy to take advice from the patients themselves as to how we do that. I know it's a bigger issue and a bigger discussion, but it's just something that we do think about in the laboratory just as much as the clinicians are within their offices as well.
Good, because Malecare has been working on that for 22 years, and we're known as the organization focused on underserved populations, not just men of color, but also LGBT and regional disparities and such, as well as not only underserved communities in the United States and economically challenged, but just people in Papua New Guinea versus Paris. What we might learn there. We're also learning that there's a racist component to that kind of thing where, it's, to blame biogenetic processes rather than societal determinants and processes and systemic racism. And that's a bigger, we're coming to understand, at least within our social work world, it seems like social determinants and systemic racism is more causal than anything biogenetic and such. But we don't know any of that absolutely yet. So it's good to have more skin samples in a lab for you guys to play around with and figure things out. Yeah. All right. So, and by the way, when the New Zealand reference to All Blacks wasn't a racial disparity thing, the name of the rugby team of New Zealand is All Blacks. I don't know why do you know why it's all blacks?
So the national bird is the kiwi, which is the feathers are black in color, and they also have the fern, which is dark. But I don't know if the All Blacks. Yeah, you're gonna make me Google this now because it's killing me.
Yeah, me too.
But I just don't know if the All Black name came from the initial kiwi bird, or the fact that their uniforms were just all black, and it was just something as simple as that their initial rugby uniform was just black jersey with black shorts and black socks.
Yeah, I mean, I heard an Australian guy tell me that. 15 years ago, last time this even came to mind, that the black uniforms are because they're too cheap to do laundry on a frequent basis.
It's easier, yeah.
Yeah, but there's a good rivalry between Australia and New Zealand, and and we'll know in a couple of weeks how that plays
that's
out.
That's right. Yeah,
we've already been trounced.
Our brothers and sisters in arms, and we that's how we act, like a family. That's how we fight. So we bicker with each other. So it's good fun though.
Dr. Ellis, thank you for spending so much time with us. I hope our patient population got a lot out of this. Like I said, you could rewind and watch. I mean, these are some of the videos that are worth watching a couple of times, if not each section, and just sort of trying to understand what we're talking about, because we're talking about us, what's going on underneath our skin. So thank you again, and hope to see you soon.
Okay. Thank you, and thanks for the work you do as well.